we have Droids that talk, Pairing Codec2 and Android. Our speaker is Joel Stanley, right here. Joel's an embedded hardware and software hacker. He's been at LCA over the past decade, playing with OLPC EXO laptops, rockets, high-altitude balloons, Arduino, and quad-core FPGA-based Game Boy emulators. He takes pleasure in bringing together signal processing, low-level hardware engineering, and high-level software. On this project, he has hacked code, soldered hardware, and held antennas to make Codec 2 usable by anyone. I'll pass on to Joel now.
Thanks very much. So my name's Joel. I'm an embedded hardware engineer, software engineer, and today we're going to talk a bit about bringing Codec 2 to Android. Just before I get started, who was in David's talk just before lunch? Great, so you guys are going to know exactly what's going on. For the rest of you, we'll give a brief overview of what David covered in his talk, just so you know what FreeDV and Codec 2 is. So today, we're here to talk about a fun project involving embedded hardware, Java, C, and radios. FreeDV, the software that we're talking about, it's a cross-platform application for doing digital voice transmissions. It uses two major software components, Codec 2, it's a low bit rate digital voice codec, and FDM-DV2, a modem for transmitting that codec over HF radio channels. And it was developed by David Rowe. So this is a screenshot of FreeDV, a bit like David showed us in the previous presentation. There you can see a waterfall of the different modem carriers transmitting the codec over the air. So the talk today is a bit about taking this technology and putting it into a handheld Android device. So here's David. So I've got a couple of different hobbies. Amateur radio and free software are pretty common themes running through those hobbies. Over the past couple of years, I've spent my free time working on Project Horus, a high-altitude ballooning project. I spoke about that along with Mark and Terry at last year's LCA, if you're lucky enough to be there. So in that project, again, there's a common theme of free software. We've got the payload software and hardware, that's both open hardware and software, as well as the receiver software you run on your PC and the distributed listener network, which is a web backend, all open source software. So in case you're not sure what Project Horus is about, on the top right there's a photo of Mark and I from the LCA 2001 dinner, where we auctioned off a print of Tux at 35 k's up over South Australia. That photo was signed by Linus and by Vince Cerf, who was keynoting, and the other keynoters from that year, and it raised about 25 grand for the Queensland Flood charity that year. The other main photo there, that's from LCA last year. Last year after I talked, we snuck out the back and let go of a balloon, and it actually landed in the middle of the bay off of Melbourne, unfortunately. So we didn't get that one back, but it was a fun day and lots of people came out to see that one. So given that background, we're going to be talking today about modern communication systems. And David came up with a great line that was in my talk abstract. Sophisticated DSP and SDR are within the reach of the average LCA attendee skill set. So I'm going to justify that statement today with my talk. Just a bit of background, DSP stands for Digital Signal Processing. It's a relatively new field, only because 20 to 30 years ago, our computers didn't go fast enough to be able to process the information in real time to be able to run these kind of codecs. So what it's all about is doing the signal processing in software instead of hardware. Software-defined radio is an extension of DSP technology, applying it to radios. So you're moving the radio hardware into software. A nice little catch cry for that is fewer atoms and more bits. Bits are pretty cheap. Atoms tend to cost a lot. You have to ship them from overseas usually. So the more software orientated we can make these projects, the more accessible they are for everyone. So as I said, free and open source software speech codecs open up new possibilities for us, new platforms and novel applications for this technology. So building a digital voice over radio system. As I said, today we're going to build a leading edge digital voice over radio system using parts from JCar, from your local electronics store, an Android phone, free and open source software for the interface, for the signal processing, and all the glue bits that hold it all together. So first, let's talk a little bit about what digital voice over radio is. It's narrow bandwidth, low bit rate, and it's carried over. You could use VHF or HF carriers. In my radio I've built here, it's a HF radio. That means anything between about 30 and 3 megahertz. What it's not GSM and it's not VoIP. So the reason I make that point is it's not the same level of quality you might expect with a mobile phone call or a Skype call, for instance. But that's because it's a much, much lower bit rate, as I'll explain in a second. And the range, due to this low bit weight, narrow bandwidth, you can shove a lot more energy into those bits you do have to transfer. And the way that works out, it means you have 1,000 times bandwidth efficiency or power efficiency over Wi-Fi, so you can go much, much further. So we'll have a bit of a discussion now about the bandwidth requirements for the codec. So here's the bandwidth of your commercial AM radio, somewhere between 10 and 20 kilohertz. That's what you listen to when you put on ABC radio in your car, for instance. Amateur radio operators, they use single sideband analog voice, and so that's about half the bandwidth, that AM radio uses. So there's some efficiency there, but the exciting part is where FreeDV fits in. So that's the third again of the SSB analog voice bandwidth. So that means you can fit 2 or 3 carriers, 2 or 3 channels using FreeDV, where you'd otherwise just have a single person using SSB analog voice. And that's what's so interesting about David's system, is that we've worked on together. So hardware radios. Up there you can see maybe a very happy amateur radio operator's desk. He's got a whole bunch of radios there. And on the right there is a schematic of one of those radios. So all this, it's not a schematic actually, it's a block diagram. All you can see there are the major components that make up the system. As you can see, there's a fair few of them, and each of those little blocks represents an entire circuit in its own right. So just to give you some perspective, this is what happens when we turn it into software-defined radio. All that stuff that's hidden behind the big blue block there becomes software. So much fewer atoms, more bits, like I said before. So the software, it's next to free. Free as in beer, and free as in speech. And the CPU cycles, once you think about how much it costs to buy a little processor, or a big processor, divided by the number of millions of instructions per second, so the calculations it does, divided by the lifetime of the processor, those cycles are worth next to nothing. And so that's why with something like a phone that's up there, and a little bit of extras, we can create a software radio. So now we're going to go through building a software-defined digital voice radio. Cover first the hardware, and then look at the software, and go into a bit of detail about how it works. So I appreciate that not everyone in the room here is an electrical engineer. I was lucky enough to study that over a time. And so we're going to go through some of the basics with you of how radios work. So here we have a radio block diagram. Pretty simple there, only 5 little blocks in our block diagram. And so we're going to look at the different signals that go through the different parts of this radio. Up in the top right there's a little empty graph. On the x-axis we've got the frequency, and the y-axis is the magnitude of the transmission. Something you'll notice is that electrical engineers like representing signals as pointy arrows. So first up, we have the HF signal coming in from the antenna. So it's up at a high frequency there. It's a relatively small magnitude signal. So the first thing we're going to do is boost that up so that our circuit can process it. So the first block there is the preamp. So as you can see, the little HF arrow got a bit bigger. The other important component that feeds into the radio is the local oscillator. So that's a signal that's generated locally by the radio. And in my radio, we're using a little crystal oscillator to generate that signal. Now comes the important part of the radio, the mixer. What the mixer does is takes the difference between the local oscillator and that amplified HF signal, and it causes a mirror to be created down at baseband of that signal. And for our purposes, baseband is just audio signals. So it's something that you can put over a wire into your sound card and process with the PC. And again, that signal's not that strong. So the next thing we're going to do there, the final block, is amplified again with another amplifier. And so now the signal has been mixed down from HF. Now we can start doing software-defined radio with it. Now that we're all first-year electrical engineering students, we can move on to how to build the hardware. So one Saturday afternoon, I got together at David's place, and we decided to build a radio that he'd taken out of a amateur radio magazine. So this is a double sideband receiver. And the first part of the radio that I built there is the local oscillator, so that red block from the last diagram. You can see the little tin can on the right there. That's the oscillator. So it's a little crystal. When you apply a voltage across it, it oscillates at 7.2-ish megahertz. And you can see that 7.2 megahertz sine wave on the oscilloscope there on the left. So a couple of hours later, and lots of hard work, we built up the various stages of the radio. Building hardware is a little bit like writing software. You want to unit test each component as you build it to make sure that it's all good. If you go and just chuck it all together, more than likely it's not going to work. So slowly building it up, testing each phase as we went, lots of coffee. And here we have the almost complete radio. It's just missing the audio amplifier on the end there. So we put this all together, and David had a radio antenna already up on his roof, and we thought, hey, let's plug this thing in, see what it can do. So we have plugged into the antenna on the roof, plugged it into Mark's laptop, running some software-defined radio software, and he could tune to the very edge of that big white bright band there. And on the edge of that band were a couple of amateur radio operators talking from Victoria. So I'm from Adelaide, so that's several hundred kilometres. And my little radio, not only were we lucky enough for it to work first time, but we also managed to turn it on just when some guys were having a voice conversation. So that was a pretty exciting moment. Just going back to our block diagram from before, just so you can understand the circuitry and relate it to the block diagram there, I've highlighted the different parts of the radio. So you've got the local oscillator and the preamp providing the two signals that are then fed into the green mixer there and then amplified by the audio amp. And so that's the radio I'm going to demonstrate to you in a few minutes over there. So now it's time to talk about the software. So at university I studied Java programming and then promptly forgot everything I knew. I'm a C programmer generally, thanks for the clap, Chris. And so, you know, I not only that, but also I didn't want to have to rewrite all of the complicated signal processing code that David had written. So the way I chose to implement on the phone was to have native C code compiled in there, and then use this bit of magic called JNI. JNI stands for Java Native Interface, and that's a way of feeding information, feeding data between C code and Java code. So that's that little cloud thing in the middle of the codec and the Android side. So initially, the idea was we'd do this the same way FreeDV worked on the PC. You just plug it into the sound card or the line in of the phone in the same way you plug the line in of the laptop, and it would just work. Turns out it's a fair bit more complicated than that, because our Android phones or your smartphone, even though it has a microphone input for those little lapel mics, every manufacturer implements the pin out slightly differently, and they require different resistances between the pins and whatnot. So you can't just make a cable and have it work on anyone's phone. I wanted this thing to be accessible by anyone. So instead, any Google employees in the crowd? Excuse me. Is this going to give me internet? No? Okay. All right, we're on. Sorry, guys. Present. There we go. All right. Not sure what we're missing there. Looks like everything's there, so we'll press on. So compared to the previous slide, we've chucked a USB sound card in there. So now the radio output goes into a USB sound card. It's digitized by the sound card, and now we have USB packets that come across that USB cable and feed into Android. That meant instead of using Android's sound recording APIs, we had to record the audio data somehow. So that was complicated because it turns out that even though Android 4 introduced these APIs for doing host mode USB, what they forgot to implement or decided not to implement was asynchronous transfer support. So that's just a type of data transport that USB uses for shuffling packets across the bus. And yeah, it wasn't implemented, so I couldn't use it. So I fell back on libUSB. It's a C library that you'll probably have on all your laptops for interfacing with various devices. And so I ended up implementing the system based on libUSB. One of the complications there was that libUSB likes to talk to the USB device directly, but under Android you have a pretty strict permissions model. So you need to integrate the C library with this Java permissions model. It gets all kind of complicated. Luckily someone else had done the work for me. So libUSB Android is a project on GitHub. Thanks very much to the person that wrote that code for me. So as I said, yeah, integrating with the permission framework there. The next two blocks, the green and the yellow block, the codec and the modem. So they use as is from FreeDV. Just copied the functions over and got them building in the Android build environment, and off they went. So that was easy. The J&I layer, the next part, this was the complicated part. So there's lots of buffers being thrown around. There's buffers coming from the USB audio, feeding into the modem. There's data coming out of that side. The modem also produces a bunch of statistics on how the channel's operating. So I also wanted to be able to feed that over to the Java side so I could display it on the screen. Finally, with that audio data, that gets pushed out of the Android device using the audio track API. So this is just the standard way of playing back audio on Java. You feed it some 16-bit samples and out it comes. The other side of it, the more complicated part, was doing the graphing. So as you saw before, FreeDV has a bunch of different graphing modes where you can visualize the data that's happening over the channel. And I think that's pretty important to having on your phone. You need it to be able to tune the radio in and just to work out the bugs in the system. So there's not a really good way of doing graphing on Android at the moment. Some people have written various libraries for doing this. One's called GraphView. It's got a fair bit of activity on GitHub, people suggesting improvements and whatnot. When I found it didn't have any support for live graphing. So it was designed to, okay, I've got a data set, let's put it on the screen and view it. In my case, though, I was continually getting samples in that I wanted to push into the screen and throw away the samples that are more than a few seconds old. So it kind of worked for the line graphs, but for doing the scatter plot, I decided to implement my own library. To a non-Java programmer, it's really scary trying to dive in there and do some custom drawing on Android. But luckily, I recommend starting with the tutorials. So there's a nice tutorial where you get a canvas and you draw a square on it and a triangle. And that evolved within half an hour to drawing some dots. And an hour later, I had this scatter plot class ready to go. So it's actually not that hard, even though it looks quite scary. So that's the system as it stands today, and I'm going to demo to that view in a moment. There's a few more enhancements to do. As you saw on the FreeDV picture from the start of the talk, there's that waterfall plot. I don't have that yet. So that's important to be able to tune the radio. So at the moment, we can't tune. So you're sampling a whole chunk of bandwidth from the sound card. And unless it happens to be that the FreeDV signal's right in the middle, you can't receive it on my system. So I want to be able to tune around using that waterfall there. There's a bunch of other enhancements as well, but I'll talk about them in a minute. So here's the software. This is the fallback plan in case my demo doesn't work, but let's push ahead and try the demo. So Mark, can you please start transmitting? So I've got Mark at the back here. So Mark's got a HF radio up the back there. He's transmitting, how much? 5 watts? Yep, 5 watts. And I've got the radio, oh, you can see it, excellent. I've got the radio here that I built, the same one we were just talking about earlier. It's got a few more bits and bobs on the edge for tuning it now, but it's the same radio that I built before. And as you can see there's the USB sound card. So the output from the radio going to the USB sound card, the USB cable from the USB sound card going into the phone there. So, unlock my phone, click start. That's not working. You transmitting, Mark?
Now that the radio is transitioning from analog to digital, much as it transitioned from AM to single sideband in the 1950s and 1960s.
So there you can hear the FreeDV transmission, the same one that Mark transmitted earlier in David's talk. We can see here the statistics coming out of the modem. So there's the frequency estimation and timing offset. Got a nice little green light as well, a blue light there to tell you that the modem's in sync. Down here we have the scatter plot. So this is plotting the symbols that come out of the modem. So the modem transmits one of 4 symbols in each carrier. And so you should be able to see 4 discrete dots there, with the 2 dots further out. They're the, I can't remember what they are, synchronization channels. In this case, the signal isn't very strong because we haven't got a very strong amplifier on the, I'll just shut that up. We haven't got a very strong amplifier on the homemade radio, but if we had a better amplifier, that'd be more spread apart, and that's how you tune the levels in your radio and make sure it's working correctly. Excuse me. So here's a bit of a clearer picture of what I was trying to show there. With on the left there, the thing's not turned on. We press the start button. Initially, there's no transmission, so the frequency estimation is just random noise because it can't find the modem sync at all. And then on the right there, we're transmitting, so the sync light turns on. The frequency estimation, that should be a bit flatter, but I'm sure I'll find that bug soon. And you can see the very small blue dots down there of the scatter plot. So that's about it for the demonstration. Might move into questions.
So you mentioned that this is something we could all build or within the reach of us. So I'm assuming this website gives us a bill of materials and a circuit diagram and some other things to go down to JCAR and pick up.
Yeah, I'll let you in on a bit of a secret. So it was the day that proposals were due for the talk for LCA, and David came up with this wonderful idea of making Codec2 work on the phone. So he sent me an email and said, Joel, let's write a proposal, and we did. And then my talk was accepted, which was exciting. But then I realised I had a lot of work ahead of me over the past few months. First getting the hardware and then the software going. Last Tuesday I got the software working for the first time on the phone. And on the weekend started writing the talk, and here I am. So now that the talk's over with, yeah, I'll definitely be writing some blog posts on my blog and the FreeDB blog and David's blog about how to replicate the system I've got. I plan to publish the application in the Android market so that you can download and play with it on your phone. That's one of the enhancements I was going to mention actually. One of the problems with it at the moment is you have to have all this set up and you have to have someone transmitting for you to be able to just play with it. But there's no reason I couldn't have a little bit of a demo mode on the phone. So you tap the record button, record some sound, then play it back to yourself just to get a feel for how the system works and how the sound quality comes out and whatnot. So yeah, I'll definitely be putting it up there, thanks.
What kind of specs do you need on the phone for this to work?
Sorry, keep it hard. So this is a Galaxy Nexus up there. All that I know is that I'm not maxing it out because it works. I did do a little bit of playing around with optimizations using the Neon instruction set, so it's a bit like SSE, but for ARM. So it is targeted towards the higher end modern ARM chipsets, but the experiments are yet to be done, whether it will work on a cheaper one.
Have you thought about dual stacking the low side so you can either have the USB or if you happen to have the magic adapter, the audio in used to put the signal in?
Yeah, that's a really good suggestion. That wouldn't be it would be pretty easy to do that, and yeah, it's a good option definitely for if you have that option.
Yeah, along those lines, I was also wondering if you've considered utilising the FM transceiver inside the phone itself.
I hadn't thought about that at all. Can it transceive or it can only receive?
Well,
Yeah.
a lot of my understanding is a lot of them are receivers, but there's a common chip that there's a bit that gets flipped and it can actually be a transceiver.
Yeah, no, I haven't looked into that at all. It's an interesting one. I mean, one of the advantages of using HF as a channel is with a few watts you can get a long way. You do have to be an amateur radio operator to do that, which I'm not yet, to my disappointment. It's on the to-do list.
So how prevalent is the USB support in Android? Do you know at all?
So Android 4 and up, this will be compatible on. That's when the host mode APIs got introduced. So if
Do you know
have
how
it
many
rooted-
phones have that?
So on the go, yeah, so it's using the host mode support. So the phone has to have on the go support. I haven't come across a phone that doesn't have on the go, because generally the chipsets all happen to be on the go, but I'm sure there'll be phones out there that don't support it. So that's a good one to look into.
Also, with using Android, like for phones that don't have host mode, the Android has the 80K. So as long as you could provide power from, or like tap it off from somewhere else to go via the USB audio card, then you could do it that way. Like that would work with almost any Android phone, like that's running a reasonably new version of Android. It doesn't have to have host mode in that case.
Yeah, so I looked into that. So initially the design, instead of having a USB sound card, it's going to have a microcontroller running the modem software. And I was thinking about using that ADK thing to transport the data up. One of the problems with that is you can't just plug a generic USB sound card in and use it, because it's not a host, but also because just USB audio in general, even though 4.1 introduced support for USB audio, you have to be a magic ADK device, so it's useless for anyone to use outside of, I don't know, that developer that implemented it, I guess. Where were we?
Okay, looks like that's about it. Thank you for the speech. And here's a little thank you gift from the organisers and Linux Australia.
Thanks very much. Thanks, everyone.